Welcome to Oceanology International. This is the special series on biogeochemistry. We've got 4 talks this afternoon, and the first to go is Nathan Lawrence, who's the CEO of A&B Sensors, and he's going to give us a talk around revolutionizing pH sensing by smart, affordable, and self-calibrating sensors.
So, as Matt said, we're going to talk about revolutionizing the pH sensing industry by developing smart, affordable, or calibration-free sensors. Our primary market is very much on the ocean side, and we were set up from the Wendy Smith Ocean Health X Prize competition, where we developed a sort of calibration-free sensor. We did quite well in that competition. We got runner-up spot in the affordability prize, and that fund really got us started as a small SME. And that was 5 years ago, and I'm just going to highlight some of the chemistry that we're using in our current sensors and the issues that we're addressing in that. First of all, why pH? Well, the Ocean Health X Prize competition was set up really to get smart, affordable, or calibration-free systems for mass deployment in the ocean. Know about ocean acidification. The ocean is a big sponge to CO2, and over many years it's absorbing more CO2, and it's slowly increasing or decreasing the pH and making it more acidic. But there's also points around that. Local variations in pH could say where there's some pollution occurring from sort of industrial pipelines. If we look further upriver, resource management of water is extremely important, and pH is the #1 chemical measurement to do that. And that's why we think there's a good market for the pH sensor. We also have an environmental impact, not only ocean acidification, but as the ocean is becoming more acidic, there's effects on the marine life. How is pH sensing done today? There's really 2 techniques. The first one is calorimetric, and this is a dye-based system. These systems are actually really good. They're really accurate. There's no way an electrochemical system can ever get this accuracy, so 0.003 pH units. However, they are like doing an experiment on a chip, and I know there's some talks later around this, where you have to actually take a sample with a dye and run your measurement response time, and they have a narrow pH range depending on the types of dyes you might use. There's the electrochemical side of it, traditionally dominated by the glass system or the ISFET system. These are conventional single-point potentiometric sensors. They have an accuracy around 0.02 pH units, and they require frequent recalibration. They need to be stored wet, and they have, again, on the ISFET, a narrow pH range. So there are some issues that need to be addressed with both technologies. On the calorimetric, window fouling, which gives you a variability in path lengths, and you can get blockage to your flow channels. And then on the electrochemical, as they're a single-point measurement, there is no smartness there in terms of the way they operate during deployment. There's storage issues. They have to be stored wet. They can't be stored dry, so you have to keep them wet right until you put them in the water. Reference electrode drift means that they require recalibration quite frequently, and I know a lot of the ones that are used today have to be sent off for calibration once a year at least. So where do we sit with our technology? Our main technology is around reference electrode drift and understanding that and monitoring that. If we look at a conventional glass pH electrode, and this technology works exactly the same for the ISFET, we have a pH sensor which has to be referenced to a reference electrode. That reference electrode is normally housed within a chamber through a sort of a membrane. Over time, ions leach from that chamber and cause drift in our reference electrode. This is dominated by the chemistry, the silver-silver chloride chemistry of the reference electrode, and you can see the redox potential will vary depending on the chloride concentration, which isn't good when you're in deployment where the chloride concentration varies. And we've spoken to a lot of end users and sensor manufacturers, and they say reference electrode drift is the #1 reason why electrodes need to be recalibrated. If we look at the current designs that are out there, there's ways of trying to minimize that drift using either double junction systems. Solid electrodes have been used. Low permeability membranes have also been explored, and there's ways of predicting that drift. However, in a real life situation, that's very difficult to do. We've tackled it in a slightly different way. We said, well, we know drift is going to happen. We're going to look at tracking the drift. So in a conventional pH sensor, you can have a pH change with time, but is that a real pH change or a drift system? Inside our system, we have a way of checking the reference potential. That's shown here, where we use what we call a voltammetry or square wave voltammetry system, where this peak potential will tell us the reference electrode potential. And by doing a simple calculation, we can get a sensor response minus a reference potential, and we get actually the real pH of the solution. So we can correct for this in real time. This has enabled us to two technologies. The first one we call the IRF, which retrofits into today's glass pH sensors and can be used for other ISCs and ISPET systems. But we also have a solid state system, and is the one that we're actually looking at deploying in the ocean. The reason we want to use this one in the ocean is because it can take pressure on the surface as a transducer, so we don't worry about pressure effects. It's robust, it doesn't be stored wet or dry, and so therefore has some significant advantages compared to sort of the ISPET or glass systems. So an S-series sensor is calibration free, it's smart, and I'll tell you why it's smart in the next slide. Rather than a single point measurement, it will give you a whole range of points, so it can tell us in situ what's happening with the sensor. We've made it adaptable for underwater vehicle deployment. Initially, we're looking for an accuracy of about 0.05 pH units. This is very much something that we're looking at developing as we're going through a sort of transition into commercialization, and measurement frequencies of 30 seconds. But that's again something that we're looking at optimize as we're going through the next 6 months or so. How does it work? And I'll move on to that in this slide. Well, on the surface of a sensor, we have an array of electrodes. We have a conventional reference electrode, which is the sort of the grey dot, which is masked underneath here. We have a series of reference electrodes, and we have a series of sensing electrodes. Our sensing electrodes use electrochemistry, which has redox potentials which are sensitive to the pH of the solution in which they're immersed. That is to say, this peak potential here is a signal to the pH of the solution. Our reference electrodes don't have that, so they're actually pH inert. This potential here purely tells us about the reference electrode potential of our conventional electrochemical system. What we do is combine the two sensors together, and we have a measurement for our reference, and we have a measurement for our pH. This difference here then gives us the pH of the solution. So although we're looking at two systems, what we're doing here is really taking out the error of reference electrode drift by combining those two electrodes together and looking at a difference rather than an absolute measurement. The reason we have an array of sensing electrodes on here is each of these electrodes actually act the same, but it gives us much longer lifetime in deployment. So at the moment, we have about 10 to 15,000 scans per array of sensors. We have much fewer reference electrodes because we have much better or enhanced chemical stability of those systems, so we don't need as many. Over the last 2 or 3 years, we built our own electronic systems, actually in-house, where we can derive or drive all our electrochemical signals. And these can be tethered to an underwater vehicle or to a battery housing, depending on how it's being deployed. It goes through our system. We have onboard saving of the data, or the data can be spat right out to the vehicle in real time, depending on how it's again deployed. And this is then connected to our transducer where everything occurs. The power consumption is around 80 milliamps when it's running, and in sleep mode around 5. It can take 10 to 20 volt DC, and it has storage facilities on there. So we try to make it as broad as possible in terms of the way it can be deployed. We've done various field trials. Very early on, we took one of our our second prototype to SAIC, which is the Finnish Environmental Research Institute, through some funding we had with them. And we did some tests on the ferry from Helsinki to Stockholm. So this is taking in water from the Gulf of Finland, which has quite low, I guess, PPT compared to the bulk ocean. And again, you can see here that we're actually getting signals from the sensor in real time. We've enhanced that further. We've looked at the noise that we're getting, and we've actually reduced that noise through iterations of our electronics. And we've done some of our own field trials about putting it into the sea on the Norfolk coast. and actually some more local river trials in a river near air facilities near Cambridge, not the River Cam, I hasten to add. But this is showing that the sensor can actually work in quite a varied range of salinities, quite from ocean sort of salinity right the way down to sort of river water salinities. We've done field trials with Blue Robotics, which is an AUV or an ROV manufacturer based in California, where we put our sensor onto their vehicle and put it around basically one of their swimming pool test tanks and then out into the on the coast of California. And again, we're getting good data back there from when the system was deployed. And we've also done work with DNOC. We're actually part of a grant with them to put the sensor onto underwater vehicle systems, combining our sensor with their spectrophotometric lab-on-a-chip systems. And this is a sensor just basically pasted off the pontoon at the NOC, and we're getting here reference and pH sensing chemistry occurring here. Our product line is shown here. We have a range of sensors, and their aim is to basically address different types of markets, I guess you might say, where we have OEM kits, which may be placed into SON manufacturers, and then standalone systems for different depth rating. I'm hastening to add, currently our S1000 and 1100 series are the ones that we've got towards the commercialization stage, and the 1200 and the 1300 is still in their development stages as we look at the pressure around the sensor. That's not to say that the chemistry is pressure. Signal is pressure independent. It does have a temperature correction, but that's calibratable as we're doing in the lab. We see pH as a first step into the sensing market. And in the future, we're looking at redox potential using IREF technology as a way of calibrating for reference electrode drift on redox potential measurements, and then looking at, in the future, oxygen sensing as electrochemical oxygen electrochemistry and oxygen actually dovetail quite well together, and you can get responses to oxygen depending on the chemistry you use. So this is a start of what we call a platform for air sensing technologies. Just to show how we've evolved over time since the X Prize competition. We have quite a notable grant with the NOC on looking at sensors for ocean acidification, as I said earlier, to put onto underwater vehicles. We've done quite well with Horizon 2020 funding, both phase 1 and phase 2, and Innovate UK funding for various projects that we've been doing. And our aim is really to take all of this technology to market in the next 6 months is what we're aiming for. Most interestingly, well away from oceans, is that we have a sensor being developed for cow boluses, so inside the cow stomach, where we use air technology that we use in the ocean in quite a different and extreme environment. Of course, we're the sum of many parts. One is through various funding that we've got during the course of our history. We have a great team behind us, all the way from our young scientists, all the way up to our older sort of electronics engineer experience in audio systems and now electrochemical systems. And we've recently got some funding from Hatch, who are in the aquaculture area, and namely a capital partners who are a set of angel investors. And I'd like to thank them all for their help and support as we've gone through our development cycle. And I'd like to thank you for your time today.
Thank you very much, Nathan. Okay, so we're going to take questions at the end. So next up is Victoire Rerol from Fluidion, who's going to talk about multi-parametric.
Hi, thanks. So I'm Victoire Rerol from Fluidion, and I will talk about the development of multi-parameter colorimetric analyzer for autonomous in situ deployment. So at Fluidion, we are a high-tech company specialized in the development of samplers and an analyzer for water quality monitoring in areas such as freshwater, lake monitoring, coastal waters, but also drinking water and wastewater treatment facilities. So here is a brief overview of our products. So we have the alert system and alert lab for our microbiology analyzers to monitor Escherichia coli, total coliform, and enterococci contamination. We have some surface water sampler, the oceanography sampler, which is meant to be deployed on underwater vehicles such as gliders, our colorimetric chemical analyzer, and finally our Freudian drone, which is a surface USV to deploy the different instruments that we've developed. So all our instruments are portable and very easy to deploy. They don't require any specific plumbing, and they are battery operated, and they transmit wirelessly, which means that you can operate remotely the instruments, either from your mobile phone or from a web platform, where all the data are gathered as well, and the data analysis is done. So you can also generate some early warning alerts in case of contamination detection. So now about our chemical analyzer. So the chemical analyzer is based on colorimetric assays, the same that are used in standard laboratory protocols for water quality monitoring. And what we do at Freudian is to use latest advanced technologies in miniaturization and microfabrication in order to move from these instruments in the lab into portable devices. And so our innovation is into combining mechanical systems and 3D printed parts to develop microfluidic systems. So here is an example of a MEMS, which is our micromixer chip. You can see it's the size of fingertips, and it allows to mix up to 4 different fluids in the volume of droplets. So although our colorimetric analyzer has been first developed for drinking water application, we now have different applications in freshwater and in seawater, which are the 2 applications we will see today. So for freshwater, we developed assays for autophosphate and ammonium sensors. So here are the characteristics of our 2 sensors, with the autophosphates, which we can measure from 0.06 up to 3 milligram per liter. And for the ammonium is from 0.02 to 1.5 milligram per liter. And all this within 1 to 4 minutes. And this concentration range has been optimized for the use that we have, that is a collaboration work with the CIAP. So the CIAP is a public wastewater utility of the Greater Paris area, and it's they have several monitoring stations all around Paris on different rivers to monitor the quality of the water. And we've done some with the autophosphate instruments. We've done some intercomparison with their certified lab. And you can see here on this graph that we got a very good intercomparison between our instruments and their lab, even at a low concentration as observed in the river around Paris, as seen on this graph here. So our autophosphate analyzer has been validated, its methodology has been validated, and now it's been installed at a river station from the CIAP here on the Seine River, and it's being currently deployed. Now for the seawater application, this is our hybrid pH sensor. So the idea here is to combine 2 different sensors that we have been mentioned earlier, so to take the advantage of both. So first, it's an electrode in order to have a continuous and fast response time with a low power consumption, and to combine it with a colorimetric analyzer to have high accuracy and long stability in time, and enable to have an in-situ recalibration of our electrode data. So here it's a setup, which was a ferry box setup plugged on the underway of the research ship. And you can recognize here, this is our colorimetric analyzer, which has been adapted for seawater measurement. But now we moved on to an in-situ version of the colorimetric analyzer. And here on this drawing, you can see here, this is a pressure-proofed housing for the electronics. And here on the left, these are the components that needs to be accessible so that they can be replaced for maintenance, such as the reagent bottle here and the tangential filter. So if we look in more details, here, this is a picture of the analyzer outside of its housing. So on the left, you can see again the reagent bottle, the pressure compensation piston. Here, this is a tangential filter, the pump head. And here, this is the inside of the housing, which is divided in two compartments. This first compartment is for the fluidics. It's oil-filled and pressure compensated. That's where you have all the valves and the mixing of the reagent and the optical cell for the measurement. And here in the second compartment, it's not pressure compensated. And that's where you have the rest of the electronics and the optics. The advantage of this approach is that you can have some fairly sensitive optics and electronics, such as here, this is a multi-wavelength spectrometer, which enables to move to other parameters in the future designs. So we checked the calibration of our analyzer. So this analyzer is running with purified metacresol purple, and we use the coefficients from the literature. We check this calibration running trace buffers, some homemade trace buffers, as well as trace buffers from the Scripps laboratory. And the discrepancy between the buffers and what was measured being lower than 10 millipH, we decided that there was no need of correction of our instruments. Then we performed the calibration of the electrode, and this is done in seawater this time. And the idea is to run in parallel the electrode and the colorimetric analyzer, and adjust the pH by adding hydrochloric acid or sodium hydroxide. And you obtain a linear response of the electrode as a function of pH. So then the instrument, the hybrid pH, was tested on the buoy in Brest, so Brest being in Brittany in France, this summer. So here is a picture of the analyzer and the electrode, which are attached to a pole, and this pole was then attached under the buoy being shown here on the picture on the right. So during this deployment, we took, so here this is a photo, an aerial picture where you can see where the buoy is, and we took sample at the buoy during the deployment, and this sample was used as a reference to check the calibration, and an offset was applied to correct our dataset to this value obtained from this sample. From the rest of the deployments, then we took more samples, but they were taken directly from the GT, where here you have a monitoring station. Then when you look at, these are the data that we obtained from this deployment. And you can see in blue, these are the data obtained from the colorimetric analyzer. In yellow, these are the data obtained from the electrode. In gray, these are the data obtained from the multi-parameter probe, which is originally installed on this buoy. And then in red, these are stars, these are the data from the samples. And what you can see is that the colorimetric analyzer and the multi-parameter probe, they both follow this decreasing trend that is observed with the samples. And also these two sensors, all the sensors, they show this diurnal pattern. But one thing is this, the electrode is not showing the decreasing trend. So there is a drift that was mentioned before that happens with the potentiometric sensors from this electrode. So then we looked at how to correct for this drift using the in situ calibration with the colorimetric analyzer. So first approach was very simple, is to use just one data every day from the colorimetric analyzer and to apply an offset on the rest of the electrode data. So that's been done here, and what you can see that, so this is the first 24 hours where you have quite important drift on the sensor. And then after that, doing this correction, once the electrode has equilibrated with the seawater, then it follows really nicely the colorimetric analyzer data, despite doing only a single point correction per day. Interestingly also is that you can see that you obtain the same amplitude of the diurnal pattern, whereas the multi-parameter probe originally installed shows much larger diurnal pattern. And here I'm not entirely sure what we're observing. I wonder if it could be maybe fouling on the sensor, which was installed already for several weeks, or something, some of this effect. But then we looked at how to improve the in situ calibration of the electrode. And to do that, we looked at the tendency of the discrepancy between the electrode data and the colorimetric data in time, and obtained a function in time, a spline that then we apply on the electrode data. So by applying this correction, we obtain this result. So we removed the first 24 hours of data since it was the equilibration of the electrode. And then you obtain the electrode data, which are really nicely fitting, again, the colorimetric analyzer data. And this time we removed some of the discontinuities we could obtain from the previous calibration method. But here it's only 1 week of data. So what's needed now is to do a new deployment with a longer data set to see how the electrode would behave on a longer term and how we can use this approach to correct the electrode data. So to conclude, at Freedom, we've developed the multi-parameter colorimetric analyzer for freshwater monitoring for autophosphate and ammonium. We developed the deep-water hybrid pH instruments, where we are still working on the characterization of the instruments and on the in situ recalibration algorithm. So the next step now is to deploy it again on the buoy for a longer term. And then once it's validated on the buoy, then we will test it on a profiler. And then the next future development would be to adapt other nutrient assays to seawater application. So that's it. I would like to thank all these people we got really great help in the development and all the testing and deployment of our instruments. And thank you. And I will take questions if you have some.
So next up is Vincent Sieben, who's Associate Professor of Electrical Engineering at Dalhousie. Yeah, that's coming through, Vincent.
Okay, perfect. Thank you. I wasn't sure. I got two screens set up in a funny way here. So yeah, hello everyone. I'm Vince Sieben, and I'm Associate Professor of Electrical Engineering at Dalhousie University, which is in Nova Scotia, Canada. So I'll state off the bat, I'm a lab-on-chip expert and specialist. I've got about 20 years of experience in making these little devices, much like what you see on my intro slide here. So this was a particular chip out of my doctorate work. So I'm dating myself a little bit because the date is on the penny. So these particular devices that are centimeters in dimension are really capable and efficient devices for handling wet chemistry. So this particular chip automated some 300 steps to perform genetic analysis. And as part of that, there's a lot of functionality that has been miniaturized, including about 20 valves that you see on the chip, miniature valves, thin film heaters, electromagnetic coils for performing particle separations. And so the field has spent the better part of 3 decades making very sophisticated pieces of technology that allow us to miniaturize and perform automated wet chemistry. I had the privilege of commercializing the very first one of these devices in the oil and gas sector. And I also had the privilege of working in autonomous underwater vehicles in that sector, looking at big yellow things at the bottom of the ocean with autonomous underwater vehicles. And what became apparent to me, very visual to me, is that you have essentially robotic vehicles or platforms or batteries wrapped in plastic with a few navigation sensors and very strict payload constraints, both energetically and physically strict constraints. And so really, I see the two as a wonderful complementary set of technologies where you have, on one hand, small devices capable of being very efficient at handling fluids and platforms that really need you to be very efficient at handling those fluids. So when I started my lab 2 years ago, I looked out and said, nitrate and phosphate could really use some furthering along in the lab on chip domain. So I decided to focus my group in part on that. So really, I guess to state the problem, and maybe that's a bit negative to say, but maybe if we look at it the other way and say the wonderful technologies we've developed to look at nutrients include things like satellites. So for example, the Aqua and Terra satellites that have spectrometers like the MODIS system on board. And really what these are doing is correlating color to the nutrient concentration. So it's a color correlation. And if you dig deep, you'll see that it's got a root mean square error of ±2 micromolar. So it tends to be a fairly coarse scatter. And it also allows us to interrogate the surface primarily, which allows us to see global patterns, but doesn't necessarily give us the ability to see the interior of our changing seas and oceans. And so, of course, many oceanographers have known this for some time, and they send out big ships. So that's the second wonderful technology we've developed. We equip ships with lab cabins and wonderful bottle collection capabilities and facilities to preserve samples. And we literally, as Ken Johnson says, put our head in the ocean and take a look at the chemistry. And so we use all of this to feed into our models, to look at the space and time domains, like one of the pictures I show here on the slide of a collaborator of mine, Dr. Finkel. And ultimately, we're looking at how the sources and sinks affect all of the biology and life cycles inside of the ocean. So really, both of these approaches cost a lot of money and aren't really giving us the spatial temporal characteristics and measurements we need. So why is that? And it comes down to the mismatch really between the available technologies and the platforms we're trying to put them on. So if you want to deploy these on Argo floats as an example, or maybe some Riptide AUVs or small vehicles, the sensor itself is big, but it's the amount of reagent that it's using that is perhaps the biggest problem. So here's Seabird's hydrocycle on the left, and you can see the tubing that they're using is the size of this man's pinky pretty much. And that leads to 77 liters of waste for 2,500 samples. Now, if you compare that to a bathtub, a North American bathtub is about 150 liters. So we're pretty much filling half of a bathtub full of reagent to perform a few thousand measurements. And so when I joined Matt's group, who's going to present next, the idea was, could we shrink the chemistry control and reactions down to a small microfluidic channel? And that is pretty much a sensor that is about the same physical size as what Seabird sells, but you got rid of the bathtub. However, we're still fairly large. If you look at an Argo in the bottom right, we're trying to figure out how we can stick one of these chemistry analyzers onto a small vehicle, and floats range anywhere from 16 liters to 30 liters and have about 5 megajoules to do 30,000 samples. So we're talking about two problems. If we want to do those 30,000 samples, we're going to have to bring the energy consumption per measurement down to under 50 joules a sample, and we're going to have to reduce the sensor size a bit. So how does lab on chip, how do you take research grade stuff and move it into the field? That's really what I've spent most of my career doing in the energy sector, and what my lab and company now do. And the idea is, how do you get all of these components? And the joke in my field is, we call it lab on chip, but is it really a chip in a lab? Because you have a 2 centimeter squared size device supported by 10 or 15 PCBs, a computer, a microscope, an optical bench, pumps, pneumatic lines. So you can see a typical gantry that will interface to one of these chips. How do you take all that and package it and wrap it and put it into a field? And so it really starts by getting rid of the microscope and the optical bench. You have to figure out how you're going to miniaturize your interrogation of a very, very small amount of fluid. So the work that I started at NOC when I was with Matt Molam, we published on this wonderful tinted technique where we could use cheap optics and glue them to the chip, like an LED and a photodiode. And that's great. Perhaps it poses some challenges for manufacturability that I'll get to in a second. So once we've glued elements or epoxied elements, optical elements to the chip, hard to service the chip, replace the chip, or manufacture in mass. And so the idea is there are some challenges to think about when we think about scaling up. But it was good enough at the time. So we moved forward. We strapped some off-the-shelf valves and solenoids around these, and I present two photos of those early day systems, if Matt recalls, of the phosphate system that I built for Francois Eric on the right, and then the nitrate system that I built with Rupert Thomas and Alex Beaton. And so we moved it to a TRL, our technology readiness level, around 4 to 6. And the better part of the last 7 years, I think Matt and his team have done a wonderful job of deploying these in multiple locations on multiple platforms and showing just how rich the data sets are that you can get out of them. But when I started my lab, I looked at the landscape and I said, one or two of the problems that I really want to solve is I don't really want to glue things to my chip, and I don't want to bolt these valves and have the energy consumption of each of these solenoids associated with that chip and the pump. So is there a way I can decouple this, and can we start thinking about scalability? So jumping to the energy side of it and looking at what are the gains, if I contextualize it with the platform and keep coming back to that, the energy use or energy per sample that a hydrocycle will do, or seabird system, is about 3,000 joules of measurement. And I have this line circled in red at the bottom. We're about 44 liters for 1,000 measurements. And if we look at the mature research / transitioning to a commercial unit now out of NOC, it's between 700 and 7,000, depending on the paper that you read, joules a sample. But we've knocked down the reagent consumption by an order of magnitude to something under 4 liters, which is great. And I somewhat failed in a way in my first prototypes in my lab. I went up to about 13,000 joules a sample because I used Raspberry Pis, which, in normal circumstances, that's great. But when we're talking 1 to 5 or 1 to 15 watts for a microprocessor, it tends to jump up your energy consumption. And so we went to bare metal microcontrollers now, and we're back down to 400 to 500 joules on our commercial units through the company I've spun out of my lab called Dartmouth Oceanology. And so really to sort of kick off now where the lab is focused, I really wanted to think, what is the next generation of lab on chip systems to do wet chemistry in a marine environment going to look like? How can we scale this to thousands or tens of thousands or more? And so the focus has been on using light guiding techniques to enhance our serviceability and manufacturability, and to address the energy consumption by moving our valving to on-chip approaches and moving our heaters closer to our optical cell with a focus on joules per sample. So the core of our lab so far now has been this inlaid optical cell technique. And what we do with this, it's much like an inlaid wood table where you take maybe cherry and push it into walnut or something to create ornate tables. We do the exact same thing with microfluidics now, where we take one material, a black plastic say, and push it into a clear plastic. And the trick comes then in how we use that inlay that we've created. We create a channel across those boundaries, which allows us to have portions of our channel clear and transmissive to light, so that we can either couple light into a channel or move light out of a very small channel, and opaque sections that block light that we really don't want from background or straight light. So in this example, I built an absorption cell where we have an LED hitting a prism, bouncing down a very narrow and long channel, hitting another prism, bouncing back up to a photodiode. And that allows us to do calorimetry and absorbance spectroscopy. But the beauty of this is that I can make the chip in a foundry or a traditional fab shop, and I can make my PCB with traditional electrical engineering tools and foundries. And I could take the two without ever having them seen each other and couple them together and have the LED and photodiode aligned to my prisms and make absorbance measurements on something that's under 10 microliters with 5 centimeter path lengths. So if we take this LED example on the top right and we shine it into one side, we can see the dot on the bottom that allows us to measure intensity changes. So we're pursuing patent protection on this. But the important thing to note is that we no longer are epoxying things to our chip, which allows us to swap out chips if we want to for different functionalities or for servicing. Secondly, we've spent a great deal of time on various microfluidic valves, flat-based and magnetic-based. And the first thing we do is we put them into vehicles and we put them out into the Bedford Basin or into testing tanks, and we pass through very nasty and particle-laden solutions and try to break them. And we characterize how many thousands or tens of thousands of actuations we can get. And so in the last 2 years, we've come to 2 approaches we're quite happy with, and we've now moved onto these check valves onto our chip. And finally, when we're heating a fluid, ultimately we're down to a few microliters or fractions of a raindrop. We really don't want to spend energy heating up a block of the chip or our chip. We're really only trying to heat up a small portion of that channel. So we really want to bring that heater as close as possible. And so we've integrated wires and deposited thin film heaters close to our channels. We've done some very innovative insulating techniques that we're in the process of writing up and patent protecting. So can't get into too many of the details here, but we've been able to go from kilojoules per sample, essentially, when we just heat the block or the chip, down to tens and hundreds of joules, which is just highly advantageous. So once we have these core elements, the optical components, the valves and the heaters, we throw them together. We have, as an example on this particular slide, 8 check valves, 3 syringe pumps, which ultimately control 4 syringes, microfluidic mixers, 2 of our special inlaid optical cells, and we perform the automated chemistry for orthophosphate in this example. And when we package that up in a can and deploy it on some of our platforms, we get some nice promo shots that look like this. And I encourage you to look up the publication that we're going to be submitting fairly soon. But the idea is we're really pushing down size. We're our best sensor is 2.5 inches in diameter, quite small compared to existing systems, and our reagent and power consumption are dramatically lower. And the nice thing is we've done this without compromising performance. So our calibrations are as good, if not better, than most of the literature out there, because it's based on 100-year-old chemistry. So we're down at 10 to 50 nanomolar, depending on the chemistry we put through our channel and our absorbent cell. And in a fairly traditional sense, we run multiple standards through it and look at the linearity for our color, our absorbance versus the concentrations of these. We've done it for nitrate and using the vanadium reduction method with our heaters. So things are looking pretty good. We decided to then cast it off the dock, and we've done a number of deployments now. And this one, I point out, it was particularly remarkable because we had one of our units deployed when Hurricane Dorian passed through Halifax. And unfortunately, the power got killed to our dock station, so we only got the portion of it. But the idea is that we still see the traditional conventional mixing where water height and nutrient concentration are out of phase with each other. So we get the well-known when we have high tide, low concentration due to dilution, and then when the tide goes out and the sources of fresh water come and reinvigorate our basin with phosphate, we end up with, in this particular case, it was fairly large, a 10 micromolar spike in phosphate concentration. Shows that the technology is now getting into the water. And when COVID hit, we've been pushing the commercialization front and have secured a couple of big contracts where we're going to be deploying 25 of these units that you see on your screen right now around aquaculture pens to monitor orthophosphate for a project called Oceanology. It's a $29 million project. Of course, our share is not that big, but it's really nice to see the technology come all the way through the paces from napkin concepts to the product. And we feel that we've got a fairly scalable model. And I'll close up the presentation just by stating that I am standing on the shoulders of a lot of wonderful and talented people. Arnold Furlong, who is our CEO of DOT. I am the CTO of DOT. Greg Johnson with RBR was an early supporter. I have a number of talented students and a couple of really good engineers that have helped us bring this from my lab out into the field. So I'll close up there, and I look forward to fielding and taking questions at the question and answer session. And this is an example of the evolution of our lab in the last 2 years. So thanks for listening.
Thanks very much. So I'm going to talk about lab-on-chip chemical sensors, which we've heard a fair amount about so far this afternoon. I'm also going to talk about some of the applications and show some of the data where those systems have been deployed. So we've heard a little bit about the drivers. The reason why we started this work in Southampton was really to address the need within glacial ocean observing, the lack of data that Vince, I think, has very ably outlined. But increasingly, we're finding that there are a number of industries which also need that data for things like environmental impact assessments, or for just process improvements, or for regulatory requirements that are now increasingly coming into some of those industries. And some of those applications can go a long way inshore. So there is a requirement for some of these measurements in rivers, lakes, pipes, and in factories. So the global ocean observing community, particularly the science community, has prioritized the measurements that it believes it needs to make and wants to make. This is also factored into this list is the feasibility of making those measurements, but these have been brought together to create the list, which is the essential ocean variables. And here's a traffic light or system for which of those can really be made routinely from autonomous or remote observing stations with the current technology. And you'll not be surprised to hear that as a research group, we're focused on the reds and the yellows very much. And I'm just going to show today some of the ones that were yellow. We've seen already today that they can be made, those measurements can be made by devices. I'm going to show some of those being done in a fairly routine high TRL setting, high technology readiness level setting. To do this development, there's been a large group with a lot of people who passed through, including some of the speakers today. It's fantastic working with creative people over many years to enable this technology to work. So our approach has been to use lab-on-chip sensors, so combining microfluidics with very reliable and high metrology standard reagent techniques. We tend to use the industry and scientific standard techniques and adapt the technology to enable that to happen rather than the other way around, to preserve the metrology and the traceability of those techniques. So one of the things that playing with those recipes can create problems with interferences and metrology, and hence we try not to do that. But we're using those standard lab analysis methods applied with lab-on-chip, all the benefits of the microfabrication, but turning that into in situ deployable systems that can go on to autonomy, including small autonomy. And I'll show some data about that. This is to address those requirements of precision, accuracy, small size, low power, able to operate at depth, and that can be extreme depths. Have a suitable measurement frequency enables that to work, and have the endurance of several months or even years, and measure multiple parameters. So we've got a few key technologies. Vince introduced the tinted cell method for creating very low cost optics. One of the beauties of this is, yes, you have to glue in your optics, but there are no prisms, no lenses. Very simple to manufacture the chip itself. The additional process is gluing in the optics, but the optics these days, LEDs are a few pence, and they very, very rarely fail. So that's a reasonable manufacturing route. The microfluidic chips are micro machined and can be made in volume relatively quickly. We have got a new mixer design which greatly improves the volume efficiency. So the volumes that we need to process have come down from some of the data that we've published to date. And then we have pressure tolerant electronics that come together to enable us to form that sensor. Here's a sort of close up, and you can see, much like some of the pictures you've already seen, you've got these absorption channels, optics there, places for valves and pumps, and all of that comes together in an integrated system that's sort of 120 millimeters in height. And actually two systems can come back to back, so you can have two different lab-on-chip devices in a single tube, and also more than one measurement can be made on a single chip. So in terms of nutrients, these are the ones that we've developed. The two at the bottom are not routinely done, but we have done. But the top four, so nitrate, nitrite, phosphate, iron 2 and iron 3, and silicate, have all now been operationally deployed. And the performance, because we're using quite long absorption cells and we're using these good standard assays, very good limits of detection. These ones are coming up. That's the kind of stuff that's being developed in our lab for trace iron and very low concentrations of ammonia. We've also developed for the carbonate system, really important for the scientific community to look at the effects of carbon dioxide dissolving in seawater. So there's a very high precision, high reproducibility pH meter The accuracy is literally determined by the reference materials we can get hold of and the accumulation of errors in measuring those. The precision is very, very good, less than a millipH. We have a DIC system and a total alkalinity system, both of which have been deployed. The total alkalinity system is the more mature of those two. And so we can do an almost complete characterization of nutrient and carbonate systems with this technology. And we've put 7 of those devices into the front end of AutoSub long range. That's the nutrients. And actually here are the carbonate system parameters, including the A and B pH sensor that we heard about earlier, all into the back of AutoSub long range, a long range autonomous underwater vehicles. But it doesn't have to be deployed like that. Here's Alex Beaton with one strapped to his back, going to deploy it in a much more low-tech scenario here. So with a solar power for power, solar panel for power, and a standard logger in a melt stream. They've been deployed on benthic landers. So this is some work with Stefan Sommer and Mustafa Yücel. Really nice to get the technology in the hands of other users, so not us, other people independently using these and getting some really nice results. They've also been deployed for a very long time. Here is a Fram Strait deployment where we deployed for a year, nitrate data being returned from under perennially covered, ice-covered areas for a whole year. We've got some really nice data. We've made it easy for oceanographers to fit these to a CTD frame. Here's a clip with an integral battery pack, so they can be clipped to a standard ship-based CTD system. And we can get some really deep sea profiles. So one of the advantages of our technology is that the electronics and all the systems are deep sea rated. Not actually that much more expensive to achieve that. In fact, now we've done it, there is really no extra expense, and means we can make measurements down to 6,000 meters. Here's some data where we've got measurements down, nitrate and phosphate down to 4,800 meters. Equally, we can make measurements on the side of rivers. Here's a testing site, Knapp Mill, Hampshire Avon in the UK. And you can see very nice correlation between the grab samples and the silicate data coming out of the sensor over an extended time period, several months here. Here's some data from that fjord work. Here's the silicated silicic acid. Again, nice long time series. And you can see that it's not directly correlated with salinity. Can you put these vehicles, these sensors onto low power vehicles? Well, yes, you can. So we've integrated with a number of different gliders, including the Webb Slocum and here a Kongsberg Sea Glider, some work done with Mayflow and Alex Vincent some time ago. About 320 microliters of sample volume for each measurement. And we were doing, the vehicle was capable of 1,000-meter dives. Obviously, the sensor can go much deeper than that. Here it is being deployed. This is the track location that it was and where we were operating. And here's some data which is published back. This is back now in 2015, so we did this quite a while ago. Nitrate data, and you can see quite clearly the nitrate drawdown in the surface ocean and some remineralization happening at depth. So, actually revealing what's going on with the biogeochemistry from a low-power autonomous platform with these systems. Here's more nitrate data. You can see the dive profile of the glider and the measurements that have been made. And over time, you see that there is this feed-in at intermediate depths of a relatively high nitrate pulse, which would be missed by ship-based sampling, for example. This is a part of the Solstice project of South Africa. In here is a similar data set on a glider, phosphate. So we can make these measurements from a glider. We have more data coming for the other sensors from small autonomy coming up. One of the things we did do recently as part of the STEM CCS experiment, which was a big European project looking at the detectability of a breach or a potential breach in a carbon capture and storage reservoir in the North Sea. So we had a deliberate release of carbon dioxide into the sediment in the North Sea, and we had every sensor that we could throw at it, looking at that to see if we could make a operational way of detecting it. And one of the nice things to come out of that was that the lab-on-chip data was sufficiently sensitive and accurate to be able to spot very low concentrations of carbon dioxide coming out of the sediments, even when there weren't that many bubbles. We did see bubbles in this experiment, but if there weren't, we would have still been able to detected the CO2 leakage. And so what you can see here is over time, the artificial leak gets turned on. You start to see these little peaks in the data. Those little peaks in the data as the tide sweeps the source of that artificial leak, the downstream chemical effect of that gets swept over the sensors as the tide direction changes. And by looking at two different sensors, because there's such high accuracy, if you look at two different sensors at slightly different heights, you can actually work out what the flux of carbon dioxide is and so what the leakage rate from that reservoir is. So fantastic, you know, our partners in the offshore energy and carbon capture and storage industry now have a tool in which they can make these measurements, and this tool can go on low power autonomy, so they can survey large areas fairly economically. The same system, this is the colorimetric pH system that we've developed. We can use a couple of dyes, but here it is going down to, again, 4,800 meters in the region of the Porcupine abyssal plain. There's a paper just coming out which will clock through all of the errors that stack up when you make these measurements, but the precision is fantastic, and the accuracy compared to buffers is very good within sort of the 5 millipH area. We didn't have representative sampling going on or co-sampling going on in this experiment, but you can see there's very good agreement with historical data sets from this area, apart from in the upper ocean where you would expect historical data to not match what's currently happening. So really, really positive. Here's some data using that system in Loch Ness. It's the salinity means that the pH sensor doesn't actually function. So we were measuring against a standard, but that enabled us to show that we had very good accuracy, 3.6 millipH accuracy and a precision sub-millipH with that system. But here is some data from that deployment here showing nitrate being measured in Loch Ness. And really sort of wrap up where are we going next. We are integrating on lots of platforms. Actually, some time ago, we integrated on a profiling float. Here is a lab-on-chip sensor integrated with an NKE Provor profiling float. We are currently integrating with Apex floats. We are integrating, here you can see sensor systems integrated with the towed body for a wave glider, and we had a Slocum glider with lab-on-chip systems integrated with it in Loch Ness recently, and hope to be doing that again soon. So in summary, we now have a multi-parameter sensor suite developed for nitrate, nitrite, phosphate, silicate, and iron, dissolved inorganic carbon, total alkalinity, and pH. And we've got some pretty mature prototypes for trace level iron and ammonia. These can operate to depths down to 6,000 meters for most of those parameters, 600 meters for the chemiluminescent iron platform. They've been integrated into a range of autonomous vehicles, and there's good protocols for doing that. And we are interested to hear about further applications, research projects and applications. And these sensors are available commercially now through a new SME called Clear Water Sensors. And there's the address for that. And that's how I'd like to conclude. Many thanks. So please feel free, panel, to jump in for questions. But I thought I would, I've got a couple here that I can get things started with. Nathan, thank you very much for your talk. I was interested in the ability of your system to measure pH very precisely and quickly. You're currently measuring order every 30 seconds. What's the current limitation on that, and how far do you think you can push it?
And the current limitation is basically because we do a number of measurements to get the pH, and it takes 30 seconds to get that off to a single sensor. What we're looking at is multiplexing them up so we can run a series simultaneously or just after each other. So we should get down to every 5 seconds, I would think, if we could do that correctly. Yeah, that's our aim. So it requires a little bit of rejigging on the electronics, but that's the aim, yeah.
Very good. And so I was intrigued by your method of using the scanning voltammetry to locate a peak and therefore use that to calibrate your reference electrode. So what sort of accuracy do you think you can look at the reference electrode potential, and how does that correlate into accuracy of pH?
So we're looking at around plus minus 1 millivolt on that once we've got the temperature calibration. So 6 millivolts is 0.1 of a pH unit. So we could do the maths, which is going to be less than 0.01 around that of a pH unit. Yeah. So that's the aim. And typically, I mean, obviously the ocean world is very specific and very precise in where it needs to be, but some wider general applications, then that's really well suitable. So yeah, it very much depends on the application at the end.
And there's a temperature correction. Does that mean that you measure temperature, you have to measure actually at the electrode tip, or is a measurement in the water sufficient?
So what we do is we tie a temperature measurement behind one of the electrodes, so we get a conducting path from front to back, and we only need to be plus or minus 1 degree. It doesn't need to be really precise, so that's good enough. And so we get real-time temperature off that, and the response time of that is really good because it's directly in contact with the solution.
Super. I'm going to pause for a minute, see if anybody else has got a question. If not, I'm going to move on then to, thank you, Nathan. I may well come back if we have time.
That's okay.
Victoire, really great to see what Fluidium are up to. Some lovely data there. Nice to see some ammonia data, which can be very difficult. Can you talk around the stability of that assay and the performance you're getting on the metrology for ammonia?
I'm sorry, but the connection is really bad. I could not hear your question, Matt.
Okay, I was inquiring about the ammonia assay and sensor that you presented. Ammonia can be quite tricky to measure. Are you able to comment on that assay and the performance of the ammonia sensor?
I think I would need you to write it on the chat, please, because it's really difficult to understand.
Right. Okay. I'll do that on the chat. Whilst we're doing that, Vince, could you unpack a little bit the heater story? Really great that you're able to get the power down so low, but perhaps you could explain why that's needed and the benefits of having heating on your device.
Sure. It actually started on our project with nitrate. We needed to get the reaction kinetics to a sufficient temperature to make that happen on a time scale that is feasible. So for our nitrate reaction, without any heat applied to it, it could be several hours. And so we had to get it to about 45 to 50 degrees to actually get the vanadium reduction method to work. And at that point, it worked really well. And to unpack it further, we've noticed we can apply that to most of the chemistries if you're willing to pay the joule budget, if it were put that way. So for many applications, just measuring temperature and knowing your correlation coefficient would be sufficient if you want to save energy. But if you would like it at a certain temperature and like to do it faster. So that necessitated it, and we've characterized it well. I can say that we have sort of an air pocket design that we use that would withstand the hydrostatic pressure. So we've simulated the crap out of that, as it were, and then proven it in tanks and shown that the cell actually holds up. So we're quite happy with that. We're at the stage now where we're going to be integrating it with the rest of the system. So if you saw on my fluid schematic, we haven't actually put the heater into our current fully automated phosphate and nitrate systems, but the plan is to bring that online in the next year or two.
Super, that's great. So Victor, I don't know whether you've managed to spot the question on the chat.
Okay. So the question about the ammonia device. So here we are using colorimetric assay using two reagents, and what's been difficult actually was the stability of the reagents, but so and also the compatibility of the reagent was one of the tricky parts, and it took quite a few months of playing around and finding different, playing with the concentration really, and also the different materials. But now it seems to be fairly stable. Now we can have it stable for several weeks in the reagent bottles. So and the measurements are stable as well.
I'm going to return to you, Vince, if I can. So the check valves look fantastic. Perhaps you could explain the significance of check valves and how that helps you reduce power and, I guess, reagent consumption in your platform, and whether you had any material compatibility issues that you had to deal with.
Yeah, no, it's a great question actually. So when we look at the LECO valves that are typically used, or any of the manifold valves that one could buy from other suppliers, even if you employ a spike and hold circuit, you're looking at several hundred milliwatts. And when you compound them for making multiple measurements or opening valves and selector valves, it's a decent part of the energy budget. I think the majority of it is from the pump, but if we could do away with active valves and put passive valves into the chip, we lower dead volume, we get rid of the energy requirement, and you can sophisticatedly route your fluid lines such that when your pumps are pulling, they're pulling from the right area, and when they're pushing, they're blocking the right areas. So it takes a little bit of tweaking, but you can get it to work, because many of these analyzers are either mixing two reagents or adding a reagent in a flow stream. And so those are pretty simple operations that you can do with passive valves.
Thanks, Vince. That's great. Really neat work. So I'm going to ask a question to all of you now, perhaps in turn. Could you comment on the benefits you found of working with end users and doing some of these high technology readiness level demonstrations?
Can I go first?
Yes, please, mate. Thank
Yeah, no, I mean, it's been extremely beneficial. So, and one, to actually attract the grant funding to make sure you've got the end user buy-in, and you can have that as part of your technology roadmap through the grant, and they can see that as like one of the milestones that you want. So that definitely helps impact your case study and your application for grant. But then just getting the feedback from the end user is invaluable. You know, you give a sensor to somebody, you think it works well, and you think it's got all the right attributes that you want, but only until you give it to somebody who's sort of familiar with using it and deploying it do you ever learn lessons. And we always say go and break it, because it's the best lesson you can ever have. So working with partners to do that and get their feedback and experience on using it and comparing it to other systems, yeah, it's completely invaluable. We really enjoy it, and it's really helped raise our TRL actually. So we can hold it at a certain TRL until we've done that stage. But now it's let us go past where we want to be and get to that commercialization stage. So yeah, that's really beneficial.
Fantastic. Victoire, if you could answer, that'd be great. Try it on the chat. Let's see. Okay, well, while she's reading that, perhaps Vince, you could comment on the applications.
Yeah, in a lot of ways, even though it was a little uncomfortable starting a company within 2 years of starting my lab, I'll say that it's been invaluable because I was unaware of the aquaculture space as an example. And of course, they're interested in early indicators for harmful algal blooms. And so if you monitor nutrients, you might be able to pick up, the drop, I guess, that we're in nutrients before an onset of a HAB. And it totally wasn't on my radar. And so that was a valuable lesson early on to learn that you got to keep your ears open to how people want to use the sensors. And as a tech developer, I tend to get right into the, like, how could I make the coolest valve? And I think people care less about that and what they're trying to answer. And that customer discovery, Arnold Furlong, my partner and the co-founder of DOT, he guides me well in that front and make sure that I don't miss any of the cues. It's been really great.
Just see if Victoire can hear. I don't know whether Victoire can hear you guys rather than me, but perhaps we could, Victoire, if you could talk about that contact with users and applications.
Okay, so yeah, so working with end users is actually really helpful, and usually they have really good tricks to teach you. So I learned a lot with the installation on the buoy and on like important rules in the choice of material and the design, really, to make it robust. I think the main thing is to move from having something in the lab, working in the lab, and having something which is robust and used by someone else is a totally different job, and that's where being in contact with the end users really helped a lot, having feedbacks on the design.
That's
What
great.
about yourself, Matt? What about yourself, Matt? How do you find working?
So yeah, I think it's you never really know what the application or the user is going to want until you actually try it. And yeah, I think I've been guilty of the same thing, making the most precise and rugged sensor known to humanity. And you go and do a demo and it's the user interface and the software and the data plotting function that becomes the key thing that the customer becomes most exercised by. So I think it's really great for really hammering out those kind of second order effects, as well as giving the technology a really good run for its money. And I think that's been a salutary lesson, is you've got to offer a complete product. It's got to be able to interface with other people's kit, and the software's got to be good enough that an inexpert can use it. You've got to send a PhD chemist out with the thing. It's not going to get as widely accepted as it could do. And I think that's that's what we've all been doing, is trying to make the devices as robust as possible, so that inexpert users can get these measurements. And I think it's going to be really transformative going forward. I'm going to hit back with another question, and then you feel free to ask me some more. So I wanted to get your guys' opinion on kind of like some great technology we've all talked about here. Are you seeing any barriers to scale up? Is there anything that could be done to accelerate scale up and getting this stuff out there in the environment, making measurements for, you know, benefit of humanity and for a number of customers?
I think from us, we've never lacked interest in what we're doing. And I think it's really just the time to get from research development through to manufacturing and commercial. It takes a certain length of time to get there. And I think that's probably the barriers. And it links to your previous question, what's the minimum viable product to get it out there, you know? And only once you get the sensor out there do you learn. And then that probably has the barrier to scale up in some ways, because there's always going to be an inertia for take up. And all you can do is get the field data out as much as you can, you write white papers, and then that's going to drive the scale up. I think there's plenty of people that are willing to take sensors and test them. I don't think we've suffered from a lack of interest in people saying, can we try it? And I think that's really good, you know, that they're ready to take a risk and compare it and try it. So I think that's really good. And we see that specifically in the ocean industry, that everyone wants to try something new, because as you say, there's a demand for all these systems.
Victoire, you comment? So again, I'm trying that over the chat. Victoire, can you cover?
Yeah, sorry for the bad connection. Barriers to scale up. I guess that's what has been mentioned by Vincent with the way the microfabrication. So I guess like if you have all the very like sensitive material, for example, with the optics, and which requires some sensitive assembly, and that's why we're working with optical fibers, and that's quite sensitive work that has to be done by someone who really knows the task. So that makes it quite high-profile instruments in the end.
Okay, great. I should probably pause to let you guys throw a question at me. Or
so, should I comment, or do you want to? I think if you permit me to take the 1,000-foot view, I have a fair degree of confidence in everybody on this call that in our respective areas we're going to nail it. And I think the challenge starts to be, how do you get your head around all the data and ensure consistency between groups and between sensors, and how do you incorporate the metadata, the standardization? And I'm facing this on a different front because we're developing environmental DNA sensors and samplers. And one of the challenges that we're having with that is the wide range of use cases and the wide range of technologies. And when you multiply them, it kind of becomes overwhelming, right? So I think as sensor developers, as companies, it might be high time, if you will, to figure out what are going to be these standards and how do each of our sensors play into a common interface. Because ultimately, if we fast forward the clock 30 years from now, or 50 years when we're long and gone, how do we make sure that the legacy and the data that we're leaving behind are useful to subsequent generations? I think that's kind of what I'm trying to think about as a sensor developer, is how does what we're doing now, there's a commercial aspect, and I think we're going to get to tens of thousands eventually, to be honest, of units out there. But if we're not in front of the data, I think it will be for naught. That's my, and I don't have an answer for it. I'm open to starting forums and discussions and trying to figure out how do we wrap our head around that beast, because biogeochemistry, it's huge. Your last summary slide, Matt, I mean, it's great. Look at all the sensors and all the tech, right? It's, how do we put, and I'm sure you're already thinking about this, but, you know, any thoughts yourself on that, or?
Yeah, so we spent a little bit of time in with European funded projects recently thinking about that kind of well, all of the elements you mentioned, I think you nailed it, right? There's a number of really key stepping stones once the sensor works. And so standardization of metrology and metadata, and how we link that data to, now in the world of science, those tend to be open access repositories for data with very defined metadata standards and ways in which that data can be post-processed and then included in models. That in itself is a tremendous task, but then industry has a different way of operating, and you also have to be able to accommodate that. However, I think there's a common root, and I think that is around some really good practice around being able to identify your sensor, its history, its calibrations over time, where it's been, what it's done, and therefore be able to track its metrology and give you confidence in the data. And although the number of sensors, I agree with you, probably will be up into the tens of thousands at some point, probably some point fairly soon, the actual quantity of data at the moment is not so huge because we're not operating at sub-seconds yet. I'm sure we're all trying to do that, but we're not doing it yet. We're talking about 30 seconds, a few minutes generally, with the exception of some of the faster stuff that we talked about. And so the data quantities currently aren't as big as, say, deep sea photography or bathymetric surveys, which are really huge data sets. However, it's coming, and once you go to DNA, absolutely. And if we start doing sequencing in situ, the amount of data is just going to be incredible. And yeah, I think, let alone all of the good stuff in making sure the data gets to a repository that people can access and understand, how are we going to visualize all of this? How are we going to include this in models that actually enable us to have some information to make a decision? And that is a whole another level. Fortunately, there's a whole community of people that are excited by that and focused on that challenge. But yes, we as sensor developers have got to preempt that conversation and start talking to that community. Very exciting that we can, see that in the medium to near term future. I think that's great. Okay, are we petering out slightly? Any more questions? I don't think I've got any that are burning. Go on, Vince.
I had one for Victoire because I really liked what I saw with a heater close to an optical cell. Could you comment a little bit more on that? Like, is it for sale? or it was on one of your slides, I think I saw a little heater beside an optical cell. Is that in your current systems? Or?
Sorry, who's that question to?
Victoire.
You might have to write it down.
Yes, please. Okay, the heaters, so they are directly integrated on the optical cell. So there was a picture of it. So this is a platinum resistor that is directly integrated on the chip, and that allows to heat directly the fluid near the fluid. Yeah.
Okay, I'm going to, we've got a few more minutes left if we need to take it. So try and think of a last question. I'm going to try and think of a last question. If you've got one, any of you now, say it now.
I have one question. I mean, we talk about standardization and interface standardization and standardization of data, but we also have the level when we're integrating with different vehicle manufacturers or different sort of end users, just taking the sensor and integrating it with what they use already in terms of the comms protocols, the power, the pinouts from different transducers or different subcom connectors. I mean, there's no standards on that. So we're always rewiring all their sensors to do that. And I think, as we all develop more and more sensors and more companies come out with new sensors, then interfacing it with what's out there in a hardware side, I think is actually quite a challenge for the sensor manufacturers. So it's an extra complication. So I think, you know, on that standard comment, there's everything from the software side all the way down to just the raw hardware of plugging the sensor in. I think that's a challenge.
Yeah, maybe I can comment now. I mean, there's been a number of attempts at trying to harmonize standards and create common interfaces that would only be done once and then could be used multiple times, and they've really not yet gained the traction that's needed in the marketplace. And so I think we, like many other people, are pragmatically using an interface that we can use to translate whatever it is at one end to what's going to be at the other. And that's not brilliant, because that translation is extra weight, extra power consumption potentially, and certainly extra reliability problems. So I think there is an opportunity to get rid of that and to have you know, much more standardized interfaces. And if you talk to the vehicle manufacturers, they recognize this, but they don't want to go through the expensive job of either developing the standard themselves or taking on board a standard that then isn't picked up by the rest of the community. So there is a bit of an energy barrier to that future. I guess what will probably happen is whoever's dominant in the market at some point will decide, but it's not always the case. You know, look what happened in computing. It's not always the dominant incumbent in the market that gets to define the standards. Yeah, it's an interesting point. Anybody else want to comment on standards?
I think there's some analogies to be learned from the robotics industry, right? I mean, if you look at the concept of middlewares like ROS and Moose and such, I think thinking about sensors from this perspective make a lot of sense as well. If we could define at least the boundaries of how the data needs to be stored into the front computer or back seat computer, sorry, of a vehicle or a platform, that would be a start. It just sort of say, like, this is how you got to fill the database up, you know, and this is how you got to talk to our backseat computer and at least get them to update their firmware. But I think you're right, Matt. You know, once people get entrenched with a system, it's got to be a significant impetus to move them. And I don't know how, that's why I brought it up as a barrier. I'm looking forward to more discussions on how to address it. And
well, I can offer a piece of hope. I think if we club together as a developer community, actually we've got quite a lot of influence over this. So maybe that's one thing we can do. We literally have got a few minutes left. So we've been blessed with some very enthusiastic partners and applications. There remain, however, some very conservative operators within ocean observing, within industry, and within other applications. What have you found as effective of overcoming conservatism when faced with a sensing platform?
That's a tough question, Matt.
I'd leave that one to the end.
Well, data, I think, is always the way to go. You know, the more data you can obviously present it to some people that are sort of more reluctant on the uptake, and I think that's the way to go. Demonstrations of the data of the systems out there, I think that's the way you can do it as well. So there's ways in a commercial way you can do that by offering incentives if you think the client's big enough to do it. So yeah, I think that's the way we're trying to address it, definitely. But definitely the data will always rule, I think. And then it goes back to our standards discussion, I guess. If you have an industry standard for your measurements, then you can use it as a way to say this is where it is and this is where it's been deployed and it's staying on that cycle.
Give Victoire a chance to read that on the chat and see if
to be honest, okay, so I missed a bit of the discussion, I think, to be able to answer that. But for me, the feeling is more, there is more demand than than people to convince at the moment. On it's really like the users are coming to us to ask for, you know, such type of sensors that with this range of parameters and things like that. So I guess what's more difficult is to get them to use it. They're looking for this kind of sensors, but then it's another step to get them to use it as a proper tool for the decision. So for example, for the drinking water facilities, they have a process for the quality check with the sample, let's say every week, and that's what they are using at the moment. And it's been now, we have a sensor that has been deployed there for more than a year, and showing that we can have much earlier warnings with our sensor, which is recording every half an hour. And they are only starting now to consider using this as a proper control system and not just an additional information. So it takes a while for them to test it and really to trust it, I guess, afterwards.
Thank you very much, Victoire. Final comment to you, Vince, and then we really are going to have to wrap up.
Yeah, I think obviously there's the regulatory compliance route, like the Clean Water Act in the US for phosphate, for example, but there are other avenues, and I think they're intensive on our end, where you have to do your homework and figure out the answer product, because I think at the end of the day, people are buying your sensor and they're hiring a job and they want an answer, green or red, yes or no. Should I move my fish? Should I not? And I think understanding the client pull, like what are they going to do? And it's hard as a sensor developer, because we're always so excited about the sensor, but what does somebody want that sensor for? And when you understand that, I think you'll be successful in pulling the conservative customers along. That's my take on it.
Thank you, everybody. That's been a huge amount of fun. I hope the audience get a lot out of that. I think it's lovely to have such great experts on one call. Thanks for your time, and thanks, everybody.
Thanks, Matt.
Thanks, Matt.